So you have liquid water. It gives you the mass flow rate. And it gives you all the statistics that you need at the exit. So let's see. Okay, so at the inlet, it's saturated liquid water. MI dot is 5 kilograms per second. And then at the exit, we have a mass flow rate of 3 kilograms per second. The pressure at the exit is 2.5 bar. The temperature at the exit is 127.4 degrees Celsius. And the speed at the exit is 30 meters per second through an exit area of 0.05 meters squared. And so we know that at the exit, so the mass flow rate at the exit is equal to the area at the exit times the speed at the exit divided by the specific volume. And this is also at the exit. And so we have 0.05 times 30 divided by the specific volume is equal to 3. And so that tells us that the specific volume at the exit is 0.5. And then we know everything we need to look up the specific enthalpies at the exit. Since it's asking for quality, you know it's going to be saturated. So you know some of it's going to be liquid and some of it's going to be vapor. So if you use the water saturation table, you didn't have to interpolate it all. It was just a line that was given in the table. And so use the pressure of 2.5 bar and the temperature of 127.4 degrees Celsius. And those two together give you a specific enthalpy for the liquid that's equal to 1.0672. And then for the liquid, that specific enthalpy is times 10 to the, you have to multiply by 10 to the minus third. So this is times 10 to the minus third. And the specific enthalpy for the gas is 0. No, we're not looking for enthalpy, sorry. We're looking for specific volume because the whole idea is we know what the specific volume is, and we're going to use the quality equation to figure out what fraction of each of the two gives us this specific volume of 0.5. So, okay, so this is the specific volume for the liquid. For the gas, it's 0.7187. And so now you can say that the specific volume that we know we have, that total specific volume, is equal to 1 minus the quality times the specific volume of the liquid plus the quality times the specific volume of the gas. And now it's just an algebra equation, and you get that the quality is equal to 0.695. Any questions about that? That's how it has to be, because the quality is telling you the fraction of gas that you have. If you switch the order of those two, you'd be measuring the proportion of liquid that you have. Any other questions? Any other questions, other numbers on the test? Okay, so um, for this one, we're treating air as an ideal gas, and it has a molar mass of 28.97 times 10 to the minus third kilograms per mole. Okay, so in SI units, the universal gas constant is 8.314. And so the gas constant that's specific to air is 8.314 divided by 28.97 times 10 to the minus third. And that gives you 286.987. And now you can use the ideal gas law. It says P times the specific volume is equal to that air-specific gas constant times the temperature in Kelvin. And I think it gives you the pressure. It's a total of 0.1 kilograms of air. Okay, so at state 1, it says that the total volume is 0.07 meters cubed. So the specific volume is 0.07 meters cubed divided by the mass of the air, which is 0.1 kilograms. And so you get 0.7 meters cubed per kilogram. For both of them, the pressure is the same. So we have 1 times 10 to the 5 times 0.7 is equal to 286.987 times T1. And that gives you a T1 of 243.91 Kelvin. And then it's the same thing at state 2. So the specific volume at state 2 is 0.12 meters cubed. That's the actual volume divided by the mass, 0.1 kilograms. And that's 1.2 meters cubed per kilogram. And so the ideal gas law says 1 times 10 to the 5 times 1.2 is equal to 286.987 T2. And so T2 is 418.14 Kelvin. And then on that one for part B, a lot of people, so for calculating the work, this was part A, but for part B, some people use the ideal gas law, like re-expressed pressure using the ideal gas law and tried to integrate that way. But it's a constant pressure, so you don't have to do that. And so the work is just equal to the integral of P dV, where this P is just constant, so it comes out of the integral, and then it's an easy integral. Any other questions on the test? Mm-hmm. Yes, that's right. Yep, it was. So you came up with, okay, so on number 4, so you had this expression, part A was just coming up with this expression, dm dt for the control volume is equal to 2 minus 0.1 t. And then it said it started at a mass of 50 kilograms, and we want to know where it empties. So if you you can write this as the integral of dm is equal to the integral of the quantity 2 minus 0.1 t dt. Integrate dm, that is just your change in m in the control volume. Integrate this one, and you can do it from 0 to t. Really, technically, I should put dummy variables in here, but I think you know what I'm talking about. So this is 2t minus 0.05 t squared. And the change in m, if you're going from 50 kilograms to 0 kilograms, this is equal to negative 50. So you can write this as 0.05 t squared minus 2t minus 50 is equal to 0. And if you solve that, I guess I only wrote down one of them, so I suppose one of the roots was probably negative, but you get that t is equal to 57.42 seconds. Okay, so negative 17.4, we know we want later in time, so. It's 0.05 because that's just using the, what do you call that, the polynomial integral rule. So t squared, and then you have to divide it by 2, so 0.1 divided by 2 is 0.05. Anything else you want to see? Okay. So we've done, so back to the first law of thermodynamics. Volume. And we have done So we've done nozzles and diffusers. And the overall story of nozzles and diffusers is that you're exchanging enthalpy for speed. And the most simplified form of the first law for control volumes for nozzles and diffusers says H at the inlet, specific H, minus at the exit is equal to 1/2 times the quantity V exit squared minus V inlet squared. And then the next one we did was turbines, right? Or was it? Yeah, turbines. And the idea of turbines, you're using those to produce work in some way. You can use it to produce mechanical work, or you can use it to generate as a generator for electrical work. And so the idea of a turbine is that you exchange enthalpy for, it's really power, I guess, because it's on a per time basis. And the most simplified form for that says the work of the control volume is equal to the mass flow rate times the quantity specific enthalpy at the inlet minus specific enthalpy at the exit. And for a turbine, do you expect that W dot to be positive or negative? Positive, because that's what it takes for the control volume to do work on the surroundings. That's what a turbine does. And so W dot CV is positive, and the enthalpy at the inlet is greater than the enthalpy at the exit. And then I did pumps and compressors together, but I'm going to separate them here. So the third one, let's say this is pumps. And usually the idea of a pump is to raise the height of a liquid. And so in a pump, you're exchanging power. You know, that's where you plug the pump into the wall, exchanging power for fluid height. Although you could also use it to pump a liquid into a higher pressure area, or you could use it to increase the speed of a liquid. In fact, in a refrigeration system, you need a pump in a refrigeration system to push a fluid into an area that has a higher pressure so that you can keep it going around. The simplest form of the equation for a pump is the work done by the control volume, dot, is equal to the mass flow rate times the quantity, G, and well, I'll write it like this, G, Z, inlet, minus GZ at the exit. It just depends whether it's a gas when you pump it or whether it's a liquid. Yeah, pumps. I don't know really if this is a hard and fast rule, but people tend to think of it as a pump if it's a liquid and a compressor for a gas. Okay, so what do we expect for the signs here? The rate of work done by the control volume, do we expect that to be positive or negative for a pump? It's going to be negative because that's power like coming from the wall or some other source being added to your system. So this is going to be negative. So what does that mean about the height? It means that Zi minus Ze has to be negative. So you can think of that as the height at the exit is greater than the height at the inlet. Yeah, yeah. Well, that sort of depends on what your system is. But so in this case, the way we think about our system, this is like a little pump that you buy at Target. Here's the wall outlet. Okay. And there's a hose coming over here that's picking up the water. And then it's pumping it out to here. And here's the water coming out. Okay. So this is the negative W dot. That's the electrical power coming in here. That's being added to the system. Everything in the hose is also part of the system. Okay, so our system here is goes all the way from there to there. Okay, so you have a low height here. You're adding power to this part of the system, and it follows all this. And when it comes out, it just has a higher height. Okay. Yep. And then the last one is a compressor. And in a compressor, you're exchanging power for enthalpy. That enthalpy increases as you're increasing the pressure of the gas using the compressor. And the simplified equation says W dot for the control volume is equal to the rate of mass flow times the quantity enthalpy at the inlet minus enthalpy at the exit. And what about the signs for this? What's the sign of the rate of work done by the control volume? That's negative, yep. So in that way, these are the same. You're taking power and putting it into the system through the cord, electrical energy usually. And then that means that the enthalpy at the exit has to be greater than the enthalpy at the inlet. Okay, so let's go through a few problems, and I'm going to just write them up here, and I want you to sort of think through them together, and then I'll go through them after you have some time to work on it. All right, so here's the first one. Okay, so let's say that we have a pump. I just got these numbers, just sort of imagining like the pump that I have in my garage. Like uh, how much mass flow is there for that. So let's say we have a pump with a mass flow rate of 0.1 kilograms per second in steady state. Um, and it's used to lift water 1.5 meters. Okay, so here's what we're doing. Here's a hot tub. Um, and here's the pump. And we have a hose like that. And then it's sending it to the drain. Okay, so the flow is going this way. And in order to get the water from the hot tub to the drain, we have to get it up this high. So we're using the pump here um, so really you can think of like let's see, let me draw it differently. Just so we can include the pump itself in the picture. Okay, so here's the pump here sitting up on top. Okay, and it's plugged into the wall. So this is the inlet. This is the exit. We really want to get the water out here, possibly even lower than this, But in order to do that, we have to get it up over the wall. And so what we really care about, like, we can think about this as um, as using this electrical energy to get the height up to this highest point that water has to get up to. Okay, so part A, using the most simplified model, um, what's the power requirement um, so to achieve that change in height? So that's the end of that one. And then for part B, now let's say that this is part of, that this isn't just going from one part of a room to another part of a room, but it's going to two different sections of some kind of machine. So now let's say, what's the electric power requirement if the pressure at the inlet is 1 bar and the pressure at the exit is 10 bar? This is water. Okay, so see if you can work through that. Please talk to each other and stuff as you go, compare answers, and then when you're done with it, I'll go through it with you. Okay, let's go through this together. Okay, so for part A, the simplified, I'm not going to go through simplifying each thing, but just the simplified equation for a pump says W dot for the control volume is equal to the mass flow rate times the quantity G times the height at the inlet minus G times the height at the exit. We have the mass flow rate. So W dot for the control volume is equal to 0.1. That's something like right around like half a cup a second. Times $9.81 times, I guess, why don't I do it like this? So 0.1, pull the G's out, 9.81, and then times the difference. So this is going to be like 0 minus 1.5, so negative 1.5. And what do you get? You get 0.14715, right? $1.47 negative. So, and this is in watts. And so that's the power requirement. It's negative because that's power you have to put into the system. Okay, so now for part B. Okay, so now we have to think about the simplifications we're going to make. We can't just use that full simplified model. So let's just start with the whole thing. So dE dt for the control volume is equal to Q dot minus W dot for the control volume plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. And now, yes. Well, in order to get that most simplified version of the equation, it has to be steady state. So I guess we're going to use that in the second one now too. Okay, so steady state makes dE dt equal to 0, and it makes both the inlet and exit mass flow rates the same. That's the two things it does. Okay, so steady state, so this goes away. This is equal to m dot. This is equal to m dot. And then we're going to assume that it's flowing through quickly, so this will go away. We're not worried about that. we're going to assume that the speed doesn't matter. And normally, we're going to, we would assume that enthalpy doesn't matter because we have the same pressure at both two places. But now the pressure is going to change. And so you know just from looking stuff up in the tables, enthalpy changes if the pressure changes, if the temperature is the same. Okay, so now it's basically, I mean, a lot of it's the same as we had before. So let me write it. We have that W, bless you, CV dot is equal to M dot times the quantity HI minus HE plus the quantity GZI minus GZE. Okay, so now we have this new thing, the enthalpy, and we have to figure out how to get that into the calculation. So how are we going to do that? Well, we could, so if we know the temperature, we could look it up in a table, but we could also just, if we assume that this liquid is incompressible, incompressible means that the internal energy is just a function of temperature. In other words, at two different temperatures, no matter what the pressures are, the internal energy is going to be the same. And we're also going to assume that the specific volume is a constant because the density is a constant. Okay, so that's really what incompressible means, is that the density doesn't change. So we need to come up with a constant value for that. It does vary a little bit with the temperature, but the density of water in SI units, liquid water, is always right around 1,000 kilograms per meter squared. So this is always around 0.001. If we had a temperature, we could look it up in a saturation table. So this is meters cubed per kilogram. There's no such thing as specific temperature. I just mean like the actual temperature that we're operating at. Okay, and now the specific enthalpy is just equal to the specific internal energy plus P times the specific volume. And so HI minus HE is equal to UI plus PI times the specific volume minus U exit plus P exit times the specific volume. You can see that since we're operating at a single temperature, UI and UE cancel each other. And you just get that this is equal to the specific volume that's shared at both of the two states times the change in pressure. We're going from 1 bar at the inlet to 10 bar at the exit. We need to put that in SI units. So that's 1 times 10 to the 5 minus 10 times 10 to the 5. So that's negative 9.99 Not that many. So -9 times 10 to the 5. And so the change in enthalpy is equal to -900. That's in joules per kilogram. And now we can put this back into the equation. So the work requirement is equal to the mass flow rate bless you. So the mass flow rate is this times HI minus HE. So that's times -900. And then plus m dot times the quantity, all this stuff. That's what we had before. So that's minus 1.4715. And so we get a value now of negative 91.4715 watts. Any questions about that? Okay. Let's just do the quiz. And then, yes. Yeah, you could have looked it up if you, I just did it this way because we didn't have the table sitting in front of us. Okay. -91. Yeah. Okay. Mm-hmm. Yeah, you can do it that way, but that's only one of the enthalpies. We're looking for the difference in enthalpies that are basically equal, right? Because the half of the other, they should be pretty close because the enthalpy doesn't vary very much with the pressure. 762.81. At the same temperature? Oh, so okay, so if you can't look up enthalpy in the saturation table because this is a compressed liquid. So you have to do it in a compressed liquid table and look it up for say 20 degrees Celsius, room temperature 20 degrees Celsius at a pressure of 1 bar, and then look it up for 20 degrees Celsius at 10 bar. Yeah, you do have that. Yes, the liquid table. Okay, well, this is a way you can do it, yeah. Any other questions?